Here's a black hole. We imagine it as an enormous, super dark region in space that pulls everything toward it. And once something falls inside, it is dragged to the central endpoint called the singularity, where everything gets squished, right? But what if we told you that's not exactly how black holes work? So what's a singularity anyway? And what really is on the other side of the pitch-black curtain? Get ready to discover a mind-bending world of black holes, where reality is way stranger than any fiction. Black holes are intricate space phenomena. Everything about them is complicated. When a large star, about 10 to 20 times more massive than the Sun, exhausts all of its fuel, the balance between gravity and pressure breaks down, and the star collapses in on itself and goes supernova. The problem with our current understanding is that we use different theories to explain phenomena happening on different scales. There's quantum field theory, which works well to explain intricate behavior of particles, ranging from atoms and down to the tiniest subatomic building blocks of matter. Apply this theory to astronomical scales, and it's of no use. For that task, scientists resort to Einstein's general relativity. Pick the right theory, and calculations generate correct answers. But black holes are tricky. At first, they're astronomical objects, large stars. And then, they quickly shrink to much smaller, sometimes quantum sizes. For example, in order for the Sun to become a black hole, it would have to be squeezed to the size of just about 1.8 miles, 2.9 kilometers, in radius. Theoretically, you can turn any object into a black hole. There's a formula that tells us how much something has to be squeezed to become one. This threshold is known as the Schwarzschild radius, and if you wonder just how tiny our planet would have to be to turn into a black hole, imagine the entire Earth as a ball with a radius of 0.35 inches, 0.88 centimeters. But what if an object's radius is 0? Traditional calculations, both math and physics, become meaningless, and so we call this phenomenon a singularity. But does such a concept truly appear in the physical world? Let's try to break it down. Consider this thought experiment. If you wanted to make the simplest version of a black hole, you'd start with tiny bits of matter floating around in space. They don't push against anything, but just hang there. So, they're like small specks of dust floating very close to each other, without moving around much. But in space, there's gravity, and so it starts pulling it all together, reducing space in between dust particles. Over time, little specks of dust start to squeeze tighter and tighter, eventually reaching a point where their combined mass and gravity grows so intense, space around them starts to compress. And this creates an event horizon, a kind of a boundary that lets things in but doesn't really allow anything to get out. This type of a black hole is called a Schwarzschild black hole. It has mass, which is just how much stuff went into making it, but it doesn't have any electric charge or spinning motion. Now, think about what happens when you cross the event horizon of such a black hole. For the sake of experiment, let's say it's large enough for you to enter with a spaceship. Once in, you panic, and try to get out by firing thrusters to accelerate back out. Physics says that regardless of the direction the ship is facing, you'll still be drawn toward the central singularity. To understand this, imagine a long, narrow corridor with no way out except through a door at the end. Once you step into this corridor, the door shuts behind you, and there's no way to open it again. The corridor has a moving walkway, much like the travelator in an airport, and it's taking you forward at the speed of light. No matter which way you try to move, either running in the opposite direction of the walkway, or moving sideways, you'll still end up being carried forward by the walkway. Or, at least, this is how scientists thought black holes acted. However, space-time gets way more complicated when you have a mass which rotates, and so far, we only know about the existence of black holes that have angular momentum, or a spin. They form from the collapse of rotating massive stars, and as matter collapses, the rotation is conserved, leading to the formation of a spinning black hole. Quantum mechanics was created to explain the strange world of miniature scales. But instead of giving us answers, it led to more uncertainty, like fluctuations in the fabric of space-time. And these quantum fluctuations play a significant role when it comes to event horizons surrounding black holes. Now, we've all heard that nothing can escape a black hole. But this is where things get tricky. Near an event horizon, particles and antiparticles spontaneously pop in and out of existence, annihilating one another almost instantly. But what if one of these particles manages to escape the stronghold of a black hole? The late great Stephen Hawking explained this with his theory of Hawking radiation. When a particle-antiparticle pair forms near the event horizon, one of them falls into a black hole while the other one escapes. And by doing so, the free particle steals energy from the black hole. If you give it enough time, and we're talking numbers impossible to imagine, 1068 to 10103. In the realm of black holes, mysteries abound, challenging our understanding of the universe. Initially, we envisioned black holes as colossal, dark regions in space that pull everything towards them, leading to a singularity where matter is compressed to infinity. However, this simplistic view falls short when confronted with the complexities of these cosmic phenomena. In reality, infinities are not part of the physical universe as we know it. When theories yield infinite results, it signifies a flaw in their simplicity. Take, for instance, a vibrating guitar string. According to basic wave behavior, its vibration would exponentially grow over time, reaching infinity and back. Yet, in reality, this doesn't occur. This discrepancy indicates a need for more sophisticated theories to explain extreme cases, such as black holes. Black holes are formed when massive stars collapse, creating an intense gravitational field. As matter is compressed to a tiny volume, a singularity theoretically forms at the center. However, recent studies suggest a more nuanced view. According to Penrose's theorem, singularities are inevitable in general relativity, indicating that geodesics, the paths of objects in spacetime, converge inside black holes, leading to singularities. This concept is further supported by Hawking's theory of the Big Bang starting as a singularity. On the other hand, Kerr's theory introduces a different perspective. Kerr black holes, which result from the collapse of rotating stars, have two distinct horizons and an inner ring singularity. The ergospheres surrounding these black holes exhibit whirlpool-like behavior, influencing nearby objects and potentially providing a source of immense energy. Unlike traditional black holes with singularities, matter around Kerr black holes follows complex, three-dimensional paths, resembling a donut shape in space. This suggests that matter doesn't necessarily fall into a central singularity but instead moves in various directions for extended periods. This new understanding of black holes challenges previous notions and opens up a realm of possibilities. Inside these spinning cosmic giants, stars that collapse to form them might still exist, following intricate paths within the black hole's gravitational field. Light and matter might also persist, creating a surreal, isolated world within the black hole. In conclusion, black holes remain enigmatic, defying simple explanations. As our understanding evolves, we're faced with the realization that the universe is far more complex and mysterious than we ever imagined.